Hey everyone, welcome to the first video for section 7.5. So now that we're through all of the basic matrixy stuff and the basic theory from the last couple days, we're now ready to go on and start actually trying to solve these constant coefficient systems. So in this first video, we're going to look at sort of what are phase plots, what are phase portraits, which are what we're going to be using for our solution some of the time. So for the stuff here, we have the side that wants to solve for the actual general solution, which is a really important thing to be able to solve for. And then there's the phase portrait side of things, which is the pictures that we got for autonomous systems. In these cases, we're going to actually be able to get both of those, and it's going to be important to be able to figure out how to find both of them for both solving initial value problems and for getting general behavior solution. So in this first video, we're going to go through what are phase portraits, what do they look like, and how can we find general solutions in a certain case. So let's go ahead and jump right into that. So for this stuff, we are going to be pretty exclusively focusing on 2x2 systems because those are easy to draw, easy to analyze, and easy to sort out as a whole. So we'll start there, and then at the end of the very end of this chapter, I'll spend a little bit of time talking about higher dimensional systems, but that's going to be very, very little spent on that. So, like I said in the intro, there are two sort of types of analysis here. There is the finding general solutions part, and then there is the autonomous system phase portrait type stuff. So phase portrait, phase line, that's the thing you should be thinking about for that sort of argument there. So, however, in either case, we get to these answers by starting to look at our nice solutions we talked about in the last couple of videos and putting them together to form general solutions to our equation. So we're going to start by looking for nice solutions and then fill things in from there. So just to define what I mean by these terms to start with. So this autonomous system, if we end up drawing a picture, and for our autonomous equations before where we had y just as a function of t, we drew our plots with y and t, and we had, equilibrium lines and your curves that kind of met them like that. This was for dy dt equals f of y. For this case, though, we're going to have two unknown functions, x1 and x2, and then a dependent variable t. So instead of drawing it y versus t, we're actually going to draw the curves as x1 versus x2, and then just note the direction of time flow with an arrow on the curve. So if something is coming into 0, we could have something like this, and this would tell us that this curve is starting out here, and it's tracking into 0 as time goes on. So we're going to draw curves on here that are basically parametrized curves, x1 of t, x2 of t. And a graph containing a bunch of these curves is called a phase portrait. And in this context, the x1, x2 plane that we're drawing these curves on is called the phase plane. If you take any higher level of physics eventually, you might see people talking about phase space or drawing things in phase space. This is what they mean, is they're kind of removing time from the equations and drawing one parameter against the other one. That's what they mean by phase space. And since we only have two variables here, we call it the phase plane. All right, if we want to start drawing our phase portraits, we better get some nice solutions at the beginning, and then we can sort of fill things in from there. So let's start looking for our nice solutions. Nice solutions to x prime equals ax, where A is a constant matrix, A11, A12, A21, A22. Now we saw in the last couple of videos from yesterday that if we look at eigenvalues and eigenvectors, we get things that live on a straight line, so that might be pretty nice. So let's give names to these things and start writing things out. So let C be an eigenvector of A with eigenvalue r. Now what this means is that A times C equals r times C. Right, that's what we mean by eigenvectors. We did some sort of system of equation stuff to reduce this to solving a system of equations to find the components of this vector C. But in the end of the day, it ends up meaning that C solves this equation. Now, what I want to do is I want to define a matrix function or a vector function. I'm going to define a function x of t to be c, the vector c, times e to the rt. And what I want to claim is that this guy is going to solve my equation. Why did I come to this? Now remember, we saw at the end of the last video where I mentioned that for eigenvectors, we know that multiplying a by an eigenvector is like multiplying by a constant. So multiplying by a constant, we know how to solve that ODE. That's just e to the rt. If y prime equals ry, then y is e to the rt, and that's just what the answer is. So we're going to do something like that. We're going to say, let's assume we're going in the direction of c, and just solve the constant ODE, y equals r, y prime equals ry. Well, so now let's plug this into our equation and see what happens. If I take x prime, what do I get? Well, c stays where it is, and then the derivative here becomes an r e to the rt. And if I multiply a times x, I get ac times e to the rt, but ac equals arc-c, so this is rc e to the rt. And these two things are equal. So therefore, this function solves my initial value problem. Or solves my, not initial value, solves my ODE system. So x of t equals eigenvector e to the eigenvalue t solves x prime equals ax just by the definition of eigenvector and eigenvalue. So in the end, we're looking for two solutions, right? If I can find two solutions, I'm in good shape, because if I have two solutions and they are different, I have a two-function equation. If I find two solutions, I should be able to meet an initial condition, assuming things work out nicely enough. So in that case, we're good. And one way this happens is if I have two real and distinct eigenvalues. Because know what I did above? I didn't assume anything particular about the eigenvector eigenvalue. I assumed that let C be an eigenvector for eigenvalue R. If I have two different eigenvalues, each of them gives rise to an eigenvector, I can use each of them once and get two different solutions. So if A has two real and distinct eigenvalues, R1 and R2, with corresponding eigenvectors C1 and C2, then x1 of t equals defined by c1 e to the r1t, and x2 of t equals c2 e to the r2t, both solve x prime equals a times x. Now, the important thing, which we haven't said yet, and we're just going to say, is that if R1 and R2 are different, then these two form a fundamental set of solutions. We're not going to prove that. You could. And the main issue comes down to the fact that if I have two eigenvectors for different eigenvalues, they have to be independent. They have to be different from each other. And x1 and x2 form a fundamental set of solutions. So therefore, we can write a general solution. General solution to x prime equals ax is x of t equals c1 eigenvector 1 e to the r1t plus c2 eigenvector 2 e to the r2t. So if A has two real and distinct eigenvalues, which means the characteristic equation for A has two real and distinct roots, then this is the general solution to our equation. It looks very, very similar to what we had for second order ODEs for single equations. Just now we have these vectors c1 and c2 in there because we're dealing with matrices and not just functions. And so again, we're not going to prove it, but this does give you a fundamental set. Because of the different eigenvectors, eigenvalues, your Wronskian is non-zero, which means we can do this and solve for any c1 and c2. So what we're going to do next, now that we have our general solution, which is important in its own right, don't forget that. Finding this is important in its own right, and that you'll have problems where you need to solve initial value problems. You need to solve for the c1 and c2, but that's just plugging in and solving again. What we're going to do in the next video is show how we can use this to draw phase portraits to get an idea for what happens, get an idea of what's going to happen for any initial condition, whether or not we actually solve it out or not. So next video is going to go into the phase portraits. All right, so that's it for this video. I'm going to have one problem throw up there for you guys where I want you to find the general solution to a matrix ODE. If you want to look ahead, there'll be examples in the third video, I believe, for this section that I'm going to go through how to do this. But if you just follow the methods above, find eigenvalues, find eigenvectors, you should figure it out just fine. So let me write that up for you right now. All right, so here's a problem for you. Find the general solution, write it out in terms of C1 and C2, and have that in the worksheet. All right, that's it for this one. Thanks for watching. In the next video, we'll go on to phase portraits.